This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome to the discussion. Today we're delving into a research paper titled Incorporating Failure of Machine Learning in Dynamic Probabilistic Safety Assurance. This paper proposes a novel framework for enhancing the safety of autonomous systems, particularly focusing on autonomous vehicle platooning. The core idea is to explicitly model machine learning (ML) failures within a dynamic safety assurance framework. Let's start with the fundamental problem. Why is incorporating ML failure crucial in safety-critical systems like autonomous vehicle platooning?
The increasing reliance on ML models in safety-critical applications introduces a unique challenge. Traditional safety assessment methods often focus on design artifacts or code, but ML models learn behavior from data, making their failures harder to predict and analyze. These failures, often stemming from distributional shifts between training and operational data, can lead to unexpected and potentially dangerous behavior. Explicitly modeling these failures allows for a more robust and realistic safety assessment.
The paper mentions SafeML. Can you elaborate on its role in this framework and how it addresses the challenges posed by ML imperfections?
SafeML is a runtime monitoring system that detects distributional shifts between the training data and the data encountered during operation. It uses statistical distance measures to quantify these shifts and assigns confidence levels to the ML model's predictions. Essentially, it flags predictions as unreliable when a significant shift is detected, allowing the system to react accordingly. This is crucial because it provides a quantitative measure of ML uncertainty, something traditional methods often lack.
The framework integrates SafeML with Bayesian networks, BNS. What are the advantages of using BNs in this context?
BNs are well suited for handling uncertainty and probabilistic reasoning. They allow us to model the complex relationships between various factors influencing safety, including ML predictions, sensor data, and environmental conditions. By integrating SafeML's confidence estimates into the BN, we can perform a more comprehensive safety assessment that accounts for the inherent uncertainty of the ML component. The BN allows for dynamic safety evaluation and system adaptation under uncertainty.
The paper highlights the application to autonomous vehicle platooning, specifically traffic sign recognition. How does the framework work in this specific scenario?
In this scenario, a convolutional neural network, CNN, is used for traffic sign recognition. The CNN's output, the predicted traffic sign, and SafeML's reliability assessment are fed into the BN. The BN then considers other contextual factors like inner vehicle distance and speed to determine the overall safety status. If SafeML flags the CNN's prediction as unreliable, the BN can trigger safety-preserving actions such as reducing speed or activating a fallback control system.
Tabor mentions the use of the Wasserstein distance and bootstrapped p-values in SafeML. Can you explain the mathematical underpinnings of this approach?
The Wasserstein distance measures the distance between two probability distributions. In SafeML, it's used to compare the distribution of in-kind data with the distribution of the training data. A larger Wasserstein distance indicates a greater distributional shift. The bootstrapped p-value provides a statistical significance test, helping determine whether the observed distance is statistically significant or just random variation. This helps avoid false positives and ensures that only significant deviations trigger a safety response.
The experimental setup involved using the German Traffic Sign Recognition Benchmark, GTSRB, dataset. What were the key findings of the experiments, and how did they demonstrate the effectiveness of the proposed framework?
The experiments showed that the integration of SafeML significantly improved the system's ability to handle ML misclassifications and distributional shifts. Even when contextual factors, speed, distance, appeared safe, SafeML's detection of an out-of-distribution OOD input caused the system to transition to a more conservative safety state. This highlights the importance of explicitly considering ML failures in safety-critical systems. The results demonstrated that the system could reliably detect and mitigate high-risk scenarios even when the ML model made incorrect predictions.
The paper mentions some limitations and future work. What are some of the key areas for improvement or further research?
One limitation is the potential for false negatives in SafeML. Future work will focus on improving the accuracy and sensitivity of SafeML, perhaps by incorporating temporal reasoning or dynamic sensitivity adjustment. Another area is integrating more sophisticated fallback strategies and countermeasure selection into the BN. Finally, real-world testing in more complex scenarios is needed to validate the framework's performance and robustness.
This has been a very insightful discussion. Thank you for explaining the intricacies of this research. The explicit modeling of ML failures within a dynamic safety assurance framework offers a promising approach to enhancing the safety and reliability of autonomous systems. The integration of SafeML and Bayesian networks provides a robust and adaptable solution for handling the inherent uncertainties of ML models in safety-critical applications. Thank you.